our first speaker is Sara Gutierrez, and Sara, I will stop sharing my screen so you can share.
Great, thank you.
And Sara will talk about consequences of the nucleation barrier on lunar core formation.
All right, is the timer ready? Yeah?
Yes, I will just put it on.
Awesome.
Right.
Hi, everybody. I'm Sara Gutierrez. I'm a graduate student at Case Western Reserve, and this is my work I've been doing with the guidance of my advisor, Steve Hauk. Today I'm going to tell you why the nucleation barrier is really important for the moon's core history and further compel new sample collection and more seismometers on the moon, as they would strengthen our models for dynamo theory and planet evolution. Okay. In the largest picture possible, this work is about understanding the great diversity in magnetic fields in our solar system. Why do Ganymede, Mercury, and Earth, bodies of such different sizes, all have magnetic fields while Venus and Mars don't? And what process could explain the distinct two-phase lunar and paleomagnetic history? However, we do know that core evolution, specifically the mechanism of a purely molten core growing solids, is key to this puzzle, which is why we are developing detailed solidification models to help answer some of these questions. So normally what geodynamicists would do is compare the slopes of the liquid metals cores, adiabat and liquidus, to determine where solids first start to form. I think of this simply as if the adiabat first crosses the liquidus at the center, the core crystallizes bottom up with pure iron solids forming and enriching the liquid with sulfur, and on the other hand, here on the right, if the adiabat first crosses the liquidus at the CMB, you get top-down crystallization, which has been often referred to as iron snow, and depending on the temperature would remelt. And both of these scenarios could drive convection. There's actually more variations of solids forming at multiple places at once or in the middle, but either way, what all of these models assume is that the core is undergoing homogeneous nucleation. And that has been the standard until 2018, when Uge et al. Pointed out the nucleation barrier paradox for the Earth. For solids to start forming continuously, they need to overcome this energy barrier. The nucleation barrier for heterogeneous nucleation requires two things. First, that the liquid's temperature be at least at or below the liquidus, and second, that some substrate be present. For homogeneous nucleation, it requires just one thing, but it's quite more difficult for it to occur, which is that the liquid supercool below the liquidus an incredible amount, a third of the melting temperature for metals, which in the context of the Earth's core would be over 2,000 degrees. The temperature drop is too cold for Earth's thermal history model, so we postulate that homogeneous nucleation is impossible for the Earth's core. And more generally, what Uge's paper demonstrated is that until a substrate is introduced to a system, the liquid can just keep cooling and cooling below the melting temperature. Here I plotted how much of the moon's core, assuming pure iron, would be cooled below melting temperature if the center is supercooled X degrees. Thus, for this compositional end member, we see that around 20 degrees would result in the entire core being supercooled before any solids start to form. Consequently, the only way the solid inner core we have on Earth could have formed is if a metal substrate survived dissolution as it sank through the core and lowered the nucleation barrier at the center. The details and feasibility of this are described in Uge's paper along with Davies et al. 2019, but what we want to know is, how does the nucleation barrier affect planets or asteroids that, because of the possible composition range they're in and their smaller size, could either crystallize bottom up or top down? Which is why we go to the moon. The moon is the optimal body to develop these solidification models we're working on because of the greater level of understanding we have for its current and past states compared to other planets. Specifically, iron-sulfur alloys have been studied extensively at the smaller pressures of the moon's core. We also have structural constraints from geodetic and seismic studies and the paleomagnetic measurements of the Apollo samples that tell us about the moon's really peculiar two-phase magnetic field history defined by an early but short and strong period, and then, instead of dying out, was followed by a super long-lasting and weak period, for which we still don't quite understand what single or combination of mechanisms resulted in this magnetic behavior. In addition, I'll say that the moon's mantle redox state and other work proposing mass anomalies in the mantle being metal chunks delivered by asteroids makes the idea that metal substrates in some capacity being available at the CMB a fair assumption. And since we don't know exactly what the interior composition or how much supercooling the core experiences, we're creating a suite of models that could be tested by a future network of seismometers, along with the hope that our timing and magnitude assumptions of the paleomagnetic field could be improved by more samples from the Artemis program. All right, so here are the results of our models for crystallization regimes if we ignore the nucleation barrier. This is straightforward. Up to about 8 weight% sulfur, the core crystallized bottom up. Above that, we'll have some ironstone regime. But if you supercool a liquid core with low amounts of sulfur, less than 8 weight%, it will supersaturate all the way to the CMB, which is what I've highlighted here. We see that only 8 degrees supersaturated the entire lunar core, which means that if a substrate is present at the CMB, solids will form at the CMB and not at the bottom of the core, as you would otherwise believe for a core with this given composition. And what we're doing here is describing what could possibly happen for a lunar core with a given composition and a given supercooling. On the very left, we have no supercooling, but it's just reached the liquidus at the very bottom and a substrate has been delivered. So this is as close to canonical growth as possible. Next, we have a core with low sulfur and it's partially supercooled, but not all the way to the CMB. So a substrate still needs to sink. And once it does, all supersaturated dust will solidify extremely quickly, basically instantaneously on lunar timescales. And then on the right, we're introducing 2 top-down end members to get at just the possible variety in substrate availability at the CMB. Either could describe a low sulfur supersaturated core or a sulfur-rich core. We have the end member here as scarce nucleation sites where dendrites don't interact with each other and then would sink, and then the other end member being where there's so many nucleation sites that it operates as a delaminating layer. And here are some of the results for how big a core would grow during just rapid growth for a low sulfur and only partially supercooled initial conditions. We see that the more sulfur rich, the smaller the core, the solid core that it grows to. And then the more it's been supercooled, the larger it'll grow to. And all of these grow on an order of 10,000 years, which is instant on lunar timescales. If a solid inner core is instantaneously formed, and then you have normal secular cooling growth that follows that, the onset of solids will be delayed significantly. We're also thinking about how for top-down plentiful nucleation sites, which I was originally skeptical of because of the likeliness of the presence of a solid layer at the CMB on the moon, we found that the mass fraction of these layers are so small, imagine a sponge 90% water, that once it sank, it would compact to a solid core, but while it's at the CMB, where it's not compacted, there's the question of how big could that extremely porous iron layer be without being detected with new seismic data? And there is the piece of how the Lunar Geophysical Network could help us rule out some of the various models we're offering. But for the purpose of this talk, what I would like you to take away is that the nucleation barrier is really important when we think about core formation. No longer can we say for small bodies whether their cores form bottom up or top down based off solely the composition. And furthermore, that a supercooled core will start to crystallize later and very quickly throughout all supersaturated depths. We're exploring currently how that would impact buoyancy flux, maybe affect magnetic field generation with some sort of pulse of energy. And lastly, my work shows that the big takeaway for how the nucleation barrier affects the Earth, where a metal substrate must be delivered to the center, is not true for small bodies with really steep adiabats, because they'll supersaturate so quickly that they can solidify at the CMB. Thank you for your time. And I finished early.
Thank you, Sara. Thank you for a lovely talk.